Hello student, how are you all? I hope you all are doing good. I am Pooja Tripathi, your teacher. So student, we have learned about the numbers in the earlier chapter also. In this chapter, we will learn about the numbers in detail. We will also learn about the algebraic expression, different divisibility rules. All this we are going to learn in this chapter. Let's see the chapter playing with the numbers, and our learning objective in this chapters are properties of parity, divisibility by 2, then parity in algebraic expression, divisibility by 4, general divisibility theorems, rule of divisibility, digital roots, and triptychon puzzles. So we are going to start with the properties of parity, divisibility by 2. In the earlier classes, we have learned the basic rule of parity, which is the classification of the number as even or odd. We know what are the even numbers and what are the odd numbers and how these behave under arithmetic operation. In this section, we will explore these rules in more depth and see how they apply in different expressions. Here we will take an example. Determine the parity in the expression 124 plus 39 plus 17. So, solution. Now we will consider the number step by step. So, first we will look at the 124 plus 39. Now we know that 124 is even number and 39 is odd number. Even plus odd is odd. That we know. Now we will add 17 to odd number. We know odd plus odd is even. Thus parity in entire expression is even. Clear? Now, activity, take the numbers 3, 4, 5 and 6. Use all the possible combination of addition and subtraction, create different expression, write down each expression and calculate its result. Observe the parity in each result. Now, what are the challenges you are going to face? Can you make the expression equal to 0 or 1 of the equal to 4? After checking, you will notice that there are 8 different combinations of the addition and subtraction for these 4 numbers. A remarkable property emerged from the exercise. All possible outcomes are even numbers. This is not just a coincidence. It reflects the underlying mathematical principle. Let us now justify the observation using proofs. So, proof by composition and parity rules. Consider any sets of 4 consecutive integers. So, 4 numbers and consecutive. Among these, there will be always 2 even numbers and 2 odd numbers. Now, consider the sums or the difference. So, odd pair, the sum or the difference of 2 odd numbers is always even. We know the sum or the difference of 2 odd numbers is always even. Even pair, the sum and the difference of 2 even number is always even. So, any expression formed from these 4 numbers can be reduced to even result plus minus even result. The final result adding and subtracting 2 even numbers is always even. Note that the symbol plus and minus means plus or minus and is used here to show that the operation can be either addition or subtraction. Next is method 2. Proof by algebraic difference. We can prove that using algebra. Let us consider 2 expressions formed from the number 3, 4, 5, 6, differing only by one sign. So, expression 3 plus 4 plus 5 minus 6, that is equals to 6. Second expression 2, 3 minus 4 plus 5 minus 6, that is equals to minus 2. Notice the only difference is that 4 plus 4 plus 4 in expression 1 became minus 4 minus 4 minus 4 in expression 2. Clear? So, you will notice the difference here, plus 4 plus 5 minus 6 become minus 4 plus 5 minus 6. So, only difference is here. Now calculate the difference between the two expressions, expression 1 minus expression 2. So, if we find out the difference, we are left with 4 plus 4, 8. So, if we solve this, we will find out that final result is 8. The difference is 8, which is even. This is because the difference is always 2 times the number whose sign changed. So, the difference is always 2 times of the number whose sign is changed. So, the number 4 sign is changed, 2 times is 8. So, result is 8 here. In general, for any expression, A plus minus B plus minus C plus minus D, changing the sign of one term, like B, changes the overall value of 2B or minus 2B, which is always even. Since we can reach any expression from another by changing one or more sign, all expressions are connected by the even difference, meaning they all share the same parity. If one expression is even, all must be even. Now the principle for the different sets of number. Is the phenomena of the uniform parity limited only to expression with the 4 integer? Let us explore by examining the set of containing 3 and 5 consecutive integer. The uniform parity of the expression formed from the consecutive integer depend on the number of odd numbers in the sets. In case 1, 3 consecutive integer. Here we are taking 3 consecutive integer. A set of 3 consecutive numbers will contain either 1 odd numbers or 2 odd numbers. So, 1 odd number, for example, consider the set 8, 9, 10. There is only 1 odd number, that is 9. Any combination of addition and subtraction, these numbers will result in the odd numbers. Now, if 2 odd numbers are there, consider the set 7, 8, 9. There are 2 odd numbers, that is 7 and 9. The sum and difference of these numbers will always be even. Thus, for the consecutive integer, the parity is consistent within the given set, but it varies between different sets. Now, case 2, 5 consecutive integer. The sets of 5 consecutive integer, such as 10, 11, 12, 13, 14, will always contain 3 odd numbers and 2 even numbers. Since there are odd numbers of odd integer, any combination of addition and subtraction will yield the odd result. From these observations, we can conclude that the principle of uniform parity is not limited for 4 integer. The resulting parity depends on the number of odd numbers in the set. Now, example 2, parity of the product. Determine the parity of 27 into 13 into 5. Solution: 27 is the odd number, 13 is odd, 5 is odd. The rule of multiplication states that the product of any number of odd factors is always odd. Therefore, the result or the product will be an odd number. Now, parity in algebraic expression. After exploring the parity in expression with a specific number, we can now extend these ideas to algebraic expression. Algebra is the powerful because it allows us to make general statement. It holds the true for any integer value of variable. In this section, our goal is to identify which algebraic expression are always even and always odd, and which can change parity depending on the values of the variable. Case 1, expression the form 2x plus 2y. The term 2x is always even because it is the product of 2 and any integer with x. So, it will be always an even number. Similarly, 2y is always even. Adding 2 even numbers, the result will be even number. Thus, the expression 2x plus 2y is always even no matter which integer x and y takes. So, whatever is the value of variable, it will always be an even number. Now, case 2, expression of the form 3p plus 5q. Now, the term 3p can be odd or even depending on the p. Means depending on the value of variable. If p is even, then the result will be even. If p is odd, the result will be odd. Similarly, with the 5q can be odd or even depending on the value of q. Since the parity of each term can vary, the sum 3p plus 5q does not have the fixed parity. It can be even for the some values of p and q and odd for the other values. Now conclusion. An algebraic expression has a constant parity only if its structure guaranteed it. Expression with even coefficient like 2x often produce constant parity. Expression with the odd coefficient like 3p can have variable parity depending on the input. Means it depends on the value of variable. Now here we will take an example. Is x plus 2 always even? That we have to find out. Test for the both even and odd values. Here we have taken the value of x as 6, even. So 6 plus 2, that is 8, even number. Now if x is odd, suppose we have taken the value of x as 2. So 5 plus 2 is 7. Since the expression is odd, right, for at least one case x plus 2 is not always even. So you have to practice all the examples. Next is divisibility by 4. To understand the divisibility by 4, let us first examine the basic properties of the number that multiplies the 4. Since 4 is an even number, any multiple of 4 is always even. This immediately tells us that odd numbers can never be divisible by 4. However, not all even numbers are divisible by 4. That we have to keep in mind. The identity which even number are divisible by 4, we can classify them on the basis of their structure. One intuitive way to visualize this by using the area model of rectangle. Now, type 1, multiples of 4, form 4k. These are the even number that can be written in the form of 4 into k, where k is an integer. Geometrically, they can be represented as the rectangular with one side of the length 4, the other side of the integer length is k. Since the perfect rectangle can be formed, these numbers are exactly divisible by 4. Now, we will take an example here. Consider the number 20. It can be represented as 4 into 5 rectangle. There is no leftover unit, confirming that 20 is the multiple of 4. You can see nothing extra here. 4 into 3, 12. We can arrange it like this. So, nothing extra is remain here. If this number 14, we can see 2 blocks are left here, extra pieces. Clear? So, 12 is divisible by 4, but this number is not divisible by 14 is not exactly divisible by 4 basically. Here we have arranged in 4 rows like this. Now type 2, even number not divisible by a 4. So not all even numbers are divisible by 4. Some are not divisible by. Here in the form of 4k plus 2, some even numbers are not divisible, not multiply of 4, multiple of 4. These numbers can be expressed as 4 into k plus 2, where k is an integer. When arranged into the rectangle with one side of the length 4, these numbers always leave 2 extra square. Because these leftover unit, they cannot form the perfect rectangle with a side of 4 and therefore are not divisible by 4. Now, divisibility by 4 in the sum of 2 even numbers. Every even numbers fall into one or two categories. Multiples of 4 are even number not divisible by 4. By adding 2 even number, there are 3 possible cases. By analyzing each, we can predict whether their sum is divisible by 4 or not. So case 1, sum of two multiples of 4. 4p plus 4q. Adding two multiple 4 always give the multiple of 4. Example, consider 8. 4 into 2. 12. 4 into 3. Their sum 8 plus 12, that is 20. That is also divisible by 4. Can be represented as 4 into 5 rectangle. Algebraically, 4p plus 4q equals to 4p plus q. Since the result is 4 times an integer is always divisible by 4. Clear? Now, in case 2, sum of two even numbers not divisible by 4, 4p plus 2 plus 4p plus 2. Adding two even numbers that are not multiples of 4 also result in the multiples of 4. Here we will take an example. Consider 14. 4 into 3 plus 2 and 10. 4 into 2 plus 2. Their sum 14 plus 10, that is 24, can be visualized as the perfect 4 into 6 rectangle. 24 is divisible by 4. Now algebraically, 4p plus 2 plus 4q plus 2 can be written like this. The sum is always divisible by 4 because it can be factored as 4 times of integer. Clear? Now case 3. Sum of a multiple and non-multiples of 4, 4p plus bracket 4q plus 2. When the multiples of 4 is added to an even number. So when we add the multiples of 4 to even number, not divisible by 4, the result is never divisible by 4. Consider 12. Now 4 into 3 and 10, that is 4 into 2 plus 2. The sum is 12 plus 10, that is 22. Have two extra units when arranged in the rectangle of width 4. So algebraically we will see, if we will arrange them, two extra, these blocks will left. The remainder when divided by 4 is always 2. So the sum is never divisible by 4. Clear? Now, sum p plus q. Suppose p and q are the multiples of d. So we can imagine that a rectangle with one side of the length d and length m and n along the other side. Placing these rectangles side by side form the larger rectangle of the length m plus n and width d. This shows the sum is divisible by d. Difference p minus q. If we assume that p is greater than q, who by removing the rectangle representing q from p, the remaining rectangles still have the width d. This confirms that the difference is also divisible by d. Here you can see, so m plus n and this is width d. If we remove this part, still it is divisible by d. Clear? Now, algebraic proof. Let p and q be divisible by d, then p minus d to r, q minus d into s, whenever r and s are integer. Sum, that is equals to p plus q minus d multiplied by r plus d into s minus d r plus s. Since r and s are integer, p q is divisible by d. And the difference is given here. Since r minus s is an integer, p minus q is divisible by d. This algebraic reasoning proves that the sum and difference of two multiples of the same integer is also multiple of the integer. Example we will take here. Application of the theorem. Suppose a number m is divisible by 7. Suppose there is a number m that is divisible by 7. Consider n equals to m plus 21 and r equals to m minus 15. Now solution for n. Both m and 21 are divisible by 7. According to the theorem, their sum is divisible by 7. Conclusion, n is always divisible by 7 because their sum is always divisible by 7 for r. M is divisible by 7 but 15 is not divisible by 7. And the theorem only guarantees the divisibility if both numbers are divisible by 7, then only it is divisible, their sum will be divisible by 7. Conclusion, r is not guaranteed to be divisible by 7. Now, key insight, the sum and the difference of two numbers are divisible by the given integer, only both numbers themselves are divisible by the integer. This principal form of formulation and for many advanced divisibility rule including the multiples of 3, 5, 9 or any integer. Relationship between divisibility factors and multiples. Theorems 2. Divisibility by factors. If an integer b is divisible by another integer k, if any integer is divisible by another integer, then b is also divisible by all factor of k. Suppose b is divisible by k, we can imagine b as a rectangle with one side of length k and the other side of length n. If f is the factor of k, then k can be subdivided smaller segments of the length f. This means the original rectangle can be perfectly split into smaller rectangle of size f into n. Hence, b is divisible by f. Algebraic expression, let b divisible by k, b minus k into n, where n is an integer, let f be the factor, so k minus f into t, where t is the integer. This is how we will write the algebraic expression. Now, substituting k from the both expression and into the expression for the b, so b equals to f into t into n. So, that is equals to f multiplied by t into n. Since t into n is an integer, b is divisible by f. Conclusion, the statement is always true. Here we will take an example. The school organizes its annual sports day. There are 120 students, they can be arranged in the group of 24 for mass drill. Can the student arrange into group of 6? Can they are arranged into group of 15? That we have to find out. Now the solution. 6 is the factor of 24, we know. Theorem 2 guaranteed that the student can be arranged in the perfect group of 6 because it is the factor of 24. Now 15 is not the factor of 24. Theorem 2 does not guarantee the arrangement into group of 15. Now theorem 3, divisibility of multiples. If the integer b is divisible by k, then any multiple of b also divisible by k. If b is divisible by k, then any multiple of b will be divisible by k also. If b is represented as a k into m rectangle, then 3b is simply 3 rectangles placed side by side. The combined rectangle k into 3m still perfectly divisible by k. Let b equals to k into m, let j be any positive integer. Consider the multiple of b. J into b equals to j multiplied by k into m equals to k multiplied by j into m. Since j into m is an integer, jb is divisible by k. So, conclusion is the statement is always true. Here we will take an example. The toy factory produces 168 toys per day, which is divisible by 12. How many toys are produced in 7 days? Is the total divisible by 12? Now, the solution is total toys in 7 days, 168. Because per day it produces 168 days. 7 days, 168 into 7, 1176. According to theorem 3, any multiple of 168 is divisible by 12. So, 1176 is divisible by 12. Now, key points, any number divisible by the factor. If any number is divisible by factor of another number, also divisible by all factors of that number. Multiplying the number divisible by k by any integer produce the number divisible by k. These principles are fundamental of the problem and involving factors, multiple and divisibility checks. Now, divisibility by composite numbers and LCM principles. In number theory, it is very important to examine the statement that appear reasonable at the first glance but not hold the average situation. Such the statements are called falsies. Idea that sound correct but fail under careful examination. One such commonly misunderstood claim is falsy. If the number BBB is divisible by k, then b must be also divisible by every multiple of k. At first, this may appear logical, but at closer look, it shows that it is not universally true. This incorrect statement reverses the logic of the valid theorem, which states that the multiples of divisible numbers remain divisible by the same divisor. However, the reverse direction does not work. Now, why the fallacy fails? Divisibility works reliably only when the divisor is smaller or equal to the dividend. The multiples of k is usually larger than the k. Even if the number is divisible by k, it does not guarantee that it will be divisible by the larger multiples of k also. To disprove the universal statement, one counterexample enough. Case where the statement happened to be true. Let b is 72 and k is equals to 8. Multiples of 8 is like 16. 16 is a multiple of 8. Now we'll check the divisibility. 72 divided by 8 gives you 9. But if we'll divide by 16, it gives 4.5. If this is fail. Let us choose an example where it works. B equals to 48 and k equals to 12. The multiple of 12 is 24. Now, check 48 divided by 12 is 4, that is divisible. 48 divided by 24 gives you 2, that is divisible. This worked because the chosen multiples is also a factor of 48. So, the statement hold in that particular case, but this is only accidental, not general rule. Case whether the statement is false, let b equals to 48. Now, k equals to 9, the multiples of 9 is 18. 45 divided by 9 gives you 5, divisible. 45 divided by 18 gives you 2.5, that is not divisible. Thus, the multiples of k is not the factor of 45, so 45 is not divisible by 18. This counterexample alone is sufficient to disprove the statement universally. If the number is divisible by k, it must be divisible by all multiples of k is not always true. This is not always true. It is therefore classified as sometime true. It's sometime true but not always. True only when the chosen multiple k is also the factor of number. Why this matter? This fallacy analysis naturally led us to the more reliable and powerful concept. The number that is divisible by 2 or more divisor must be divisible by their LCM. So, the number that is divisible by 2 or more number, that must be divisible by its LCM also, not merely by each other divisor individually. This forms the foundation of the least common multiple or LCM rule, which is widely used in the divisibility test, fractions, simplification and solving number based word problems. Now, principle 4, LCM based divisibility principle. If a whole number p is exactly divisible by two integers, say a and b, suppose the integers are a and b, then p is also divisible by their LCM of a and b. This principle helps to clear up a very common misconception. Many students believe that if a number is divisible by both a and b, it must be automatically be divisible by their product a into b. This assumption is not always correct. And the LCM concept helps us to understand why. 4 column 3 rows, 6 column 2 rows, 12 divided by 4 gives you 3 and 12 divided by 6 gives you 2. Why the LCM is required? To see why the product is not always the correct choice. Consider the integer 5 and 10. So, we have taken two integers 5 and 10. The number like 20 is divisible by both. It is divisible by 5 and 10 also. A number 20, it is divisible by 5 and 10, both numbers, however, their product. So, the product of 5 into 10, that is 50. 20 is not divisible by 50. Number 18 can be arranged as a 3 into 6 rectangle or 2 into 9 rectangle, but it cannot be rearranged into the structure requiring the side length of 18, which would represent the product of the two numbers 2 into 9, 18. Thus, divisibility by 3 and 6 ensure divisibility by their LCM, not by their product. So, it is divisible by their LCM, but not by their product. This proves that the LCM, not the product, is the correct measure when checking the combined divisibility. Under what condition can we replace LCM with the simple product A into B? Now, this depends on the relationship between the two divisor. Situation 1, when the numbers are co-prime numbers. If the numbers are co-prime numbers, they do not have any other common factor than 1. Two numbers are co-prime if they share no common factor other than 1. When A and B are co-prime number, LCM of A and B, that is equals to their product. A number divisible by A and B is divisible by their product is always correct. Example A, if the number is divisible by 7 and 9, must it always be divisible by 63? Their product? Yes, because 7 and 9 are co-prime numbers. Seven and 9 no common factor other than 1, they are co-prime number. So, this divisibility of 7 9 ensure the divisibility of 63. So, you will practice all the examples. Next is connecting parity with divisibility. To complete our exploration of journal mathematical theorem, let us examine a statement that blend two important concepts, that is parity, even and odd nature of the numbers, and the divisibility rule. This example shows how different mathematical ideas can work together to form the complete logical argument. If you add an odd number to an even number, the result will be the multiple of 6. This claim eventually involved two separate conditions. What the result should be in term of parity, what the result should satisfy the term of divisibility by 6. To check whether the statement is valid, both the condition must be agreed. Let us analyze them separately. First, we will check the parity examination. From basic number property, we know that an even number can be written as 2p and odd number can be written as 2q plus 1. When we add the even and odd number, the result will be odd. So, the sum must always be odd no matter what the integer or we choose. Divisibility by 6, the number is the multiples of 6 if it can be written as 6, 12, 18, 24. Every multiple of 6 is always the multiple of 2 because 6 is equals to 2 into 3, therefore, every multiple of 6 is even. Thus, for the number of divisibility by 6, it must certainly be even number. Parity rule says the sum is odd. Now, divisibility rule says the sum must be even. But a single number cannot be odd or even at the same time. This contraction indicates that the statement cannot ever be true. It will not always be true. Algebraic demonstration. To strengthen our conclusion, let us verify the algebraically using the different variable than in original text. Even number 2 into a, odd number 2b plus 1. According to the given statement, their sum must be equal to the multiples of 6. Let us the multiple of 6, 6k. 2a plus 2b plus 1, 6k. 2a plus 2b plus 1 minus 6k equals to 0 and 2. a plus b minus 3k minus 1. The left hand side is twice an integer, so it's always even. The right hand side minus 1 is odd. It is impossible for the even number to equal to odd numbers. Therefore, the equation has no integer solution. Adding an odd numbers to an even numbers give the multiples of 6 is never true. It fails because the parity of the sum contradicts the required parity of the numbers divisible by 6, that is even number. Next is learning point 5.1. So, you have to practice all the questions given here. Next is rules of divisibility by 2, 5, 10, 4, 8, 3 and 9. Understanding divisibility through the place value. Many divisibility rules rely on how numbers are built using power of 10. Now, take a 4-digit number represent as WXYZ. Using the place value, it can be expressed as 1000W plus 100X plus 10Y plus Z. According to the place value, now factor out 10 from all except the last term. So, it will be equal to 10 multiplied by 100W plus 10X plus Y plus Z. Let the expression inside the bracket k, then the number become 10k plus z. Then the number will become equals to 10k plus z. This representation helps us to understand the divisibility rule. First is divisibility by 10. An expression 10k is always divisible by 10. So, for the whole number 10k plus z to be the divisibility by 10, the final digit z must be divisible by 10. So, the only single digit that satisfies is 0. So, rule, the number is divisible by 10 if its unit digit is 0. If unit digit is 0, then the number is divisible by 10. Now, divisibility 2, since the 10 is the multiple of 2, we know 10 is the multiple of 2 and the term 10k is automatically divided by 2. Thus, the entire number is divisible by 2 only if the last digit is even, 0, 2, 4, 6 or 8, then the number is divisible by 2. A number is divisible by 2 if its last digit is even. Now, divisibility by 5. The same reasoning applies. The term 10k end with 0 and the last digit z determine the divisibility by 5. The only digit that are divisible by 5 are 0 and 5. So, rule is the number divided by 5 if its unit digit is 0 and 5. If the unit digit is 0 and 5, that means the given number is divisible by 5. Now, divisibility by 4. To check the divisibility by 4, we recognize the 4-digit number WXYZ as like this. Since 100 equals to 4 into 25, the first part is always divisible by 4. Therefore, the divisibility depends entirely on the last 2 digit. It is the number 10y plus z. So, rule is the number is divisible by 4 if its last 2 digit. If the 2-digit number formed by its last 2 digit is divisible by 4, then the number is divisible by 4. Divisibility by 8. Use the similar idea but group the number differently. Now, group like this, 1000 equals to 8 into 125. The first term is always divisible by 8. Thus, the entire number is divisible by depend on the last 3 digit. So, what is the rule? A number is divisible by 8 if the number formed by the last 3 digit is divisible by 8. Then it is divisible by 8. Now, divisibility by 3 and 9. The rules follow the completely different principle, the sum of the digit. Rule for 9, the number is divisible by 9 if the sum of digit is divisible by 9, then it is divisible by 9. For 3, the number is divisible by 3 if the sum of digit is divisible by 3. Now, we will take an example here. We have to check whether the given number is divisible by 9 or not. We know if the sum of the number is divisible by 9, the number will be divisible by 9. So, we will find out the sum of the number, that is 26, and 26 is not divisible by 9. That means the given number is not divisible by 9. Why the rule work? Every power of 10 is just 1 more than the multiple of 9. 10, 9 plus 1. 100, 99 plus 1, 1000, 999 plus 1, and so on. Now, let us prove the rule using the 4-digit number. Rewrite each power of 10. So, 1000 can be written as 999 plus 1 into P, then 99 plus 1, we can write 100 like this, then 10 can be written as 9 plus 1 R X. So, now we will expand. Now, group the term. Now, we will group the term. So, the first expression is always divisible by 9. You can see the first expression is always divisible by 9, this expression. The second expression is the sum of the digits, so the divisibility entire depend only on the digit sum. Now, divisibility rule for 11. The test for checking whether the given number is divisible by 11 is quite different from the rule you have learned for the number 2, 5 and 10. Instead of only observing the last digit, the sum of the digit, this rule uses the pattern of alternative addition and subtraction. A number is divisible by 11 if the difference between the sum of digits at the odd place and the sum of digits at even place counted from the right hand side, you have to count from the right hand side, is either 0 or the multiple of 11. We will take an example, we will help it with the example. So, we have to check whether the given number is divisible by 11. So, for that we have to find out the sum of digit at even place and the digit of odd place separately. Start from the right hand side. 5, 9 plus 4, that is 18. These are the digit at odd place. Now, the sum of digit at even place, that is equals to 10. So, we will find out their difference, that is 18 minus 10, 8. Now, since 8 is not 0, neither is multiple of 11, that means the given number is not divisible by 11. Clear? So, you will practice all the example. Now, since 11, this rule comes from the structure of the base of 10 number system. When the number are expressed in the power of 10, the remainder follow the predictable pattern when divided by 11. Observe the power of 10. 10 is power 0, that is equals to 1. Remainder is plus 1. 10 is power 1, that is equals to 10. 11 minus 1, remainder is minus 1. So, it will follow this pattern. So, when the powers 10 are divided by 11, the remainder alternative is plus 1 and minus 1. Explanation using the 5-digit number. Let us consider a 5-digit number written as PQRST, that is 10,000P, 1000P, 100R, 10S and T. Replace each power of 10 using the 11 base form. So, 10,000 can be written as, so 10,000 can be written as 9,999 plus 1, 1000 can be written as 1001 minus 1, 100 can be written as 99 plus 1 and 10 can be written as 11 minus 1. Substitute these. Now, expand. So, we will expand it, we will get this. Now, we will group the terms. Now, what will we find out? If we group the term, the part A, this is the part A, the entire part is clearly divisible by 11. This is the part 2. This is nothing but the alternative sum of the digit or the difference between the sum of digit of even and odd place. Since part A is always divisible by 11, so whole number is divisible by 11 only if the part B is 0 or the multiple of 11. The number is divisible by 11 itself. Clear? So, for the number should be divisible by 11, the sum of digit of even place and the sum of digit of at odd place, their difference should be 0 or the multiples of 11. Clear? This elegant pattern arises directly from how number behave in the base of 10 system and the alternating remainder pattern of power of 10. Now, divisibility by composite numbers. When we want to check whether the number is divisible by a composite number, we can break the problem into smaller parts. The composite number can be expressed as the product of two or more co-prime factors. The number will be divisible by the composite number only if it is divisible by each of its co-prime factor. Then only it will be divisible by the composite number. This idea is based on the LCM rule, which state the two numbers A and B are co-prime, then the LCM will be equal to their product. Therefore, if the number is divisible by both A and B, that must be divisible by their product also. Here we will take an example. How can we check the divisibility by 12? The number 12 have the factor 1, 2, 3, 4, 6 and 12. Choose the pair of co-prime factors, that is 3 and 4. They have no other common factor than 1. Thus, the number is divisible by 12 if only if it is divisible by both 3 and 4. So, test for divisibility test for 3, the sum of digits is divisible by 3, and for 4, the number formed by last two digits should be divisible by 4. If both conditions satisfy, the number is divisible by 12. Next is learning point 5.2. So, you have to practice all the questions given here. Next is digital roots. As we continue exploring divisibility and the number properties, we come across an interesting concept known as the digital root, which is closely connected to the sum of the digits rule. Understanding the digit root can be simplified various calculations and provide insight number pattern. The digital root of the number is the single digit value obtained by repeatedly adding the digit of the number until only one digit remains. This iterative process involves the summing of the digits of the number, then summing of the digit of resulting number, and so on until the single digit number achieved. So, we will see the step to find the digit roots of the number. Add all the digits of the number and check the sum. If the single digit number 1 through 9, this number is the digit root. If it is more than one digit, repeat the process using the new number. Continue repeating the process until the single digit number is obtained. So, we will take an example here. Find the digit root for the given number. So, first we will find out the sum of digits, that is 24. The result is not a single digit number. So, we will add them. 2 plus 4, 6. Now, 6 is a single digit number. So, conclusion, the digital root for the number is 6. This is how we can find the digital roots. Digital roots are not only useful in checking the divisibility but also appear in the number puzzle, magic tricks, and even in some properties of the modular arithmetic for the example of the number divisible by 9 if only the digital root is 9. Similarly, the root can help us to quickly estimating the sum and difference of the large number. Now, the application of digital root in divisibility check. Digital roots are not just an interesting mathematical concept, they provide a practical tool for quickly checking divisibility, especially by 9. Now, the principle of the digital root of division by 9. The digital root for any number can be understood would add the remainder obtained at the number divided by 9. There is one special case. If the digital root of 9, this corresponding to the remainder 0, meaning the number exactly divisible by 9. This principle works for the same reason as the sum of digit rule. The number and the sum of the digit leave the same remainder when divided by 9. Since the digital root is calculated by repeatedly summing the digits, it shares the property making it the reliable tool for the divisibility check. So, we will understand this with the help of example. We have to determine the divisibility of the given number with 9. Solution, first we will find the digital root. We will find the sum of all digits 27, that is a 2-digit number. So, we will make it single digit number 2 plus 7, that is 9. 6 is a single digit number, the digital root of 9, which means the remainder is 0. Therefore, the given number is divisible by 9. 9 is a single digit number, so we can say it is divisible by, the given number is divisible by 9. Next is using digital root to check calculation. Digital root can also serve as a quick method to verify the correctness and large calculations such as the addition and multiplication. The rule is simple. The digital root of the result should be equal to the digital root obtained by performing the operation of the digital root of the number involved. We will take an example here. Verify the sum of these. Solution: find the digital root of the numbers being added. So 746 digital root is 8. For the number 385 digital root is 7. Add these digit roots to find the digit root of the sum. So that is equals to 15, 1 plus 5 is 6. Find the digit root of the calculation digit result. So that is equals to 1, 1, 3 plus 1, that is equals to 6. Clear? So what is the conclusion? Both result matches. Both result is equals to 6, indicating the sum is likely correct. This method is particularly useful when dealing with the long calculation or when checking multiple operation. It can quickly reveal error and save the time without performing the full calculation again. Now, cryptothem puzzle. So, a cryptothem, sometimes called a alphametric puzzle, is a type of mathematical puzzle where the digital is an arithmetic problem are replaced by letters. The main goal is so to figure out which digit each letter represents by using the logical reason and the principles of arithmetics. Now, introduction to cryptotheorems. Solving the cryptotheorem involve identifying the unique digit of the corresponding of each letter. This is not the matter of the guessing, but rather the step-by-step process of deduction based on the specific rule and the arithmetic pattern. To ensure the cryptotheorem has a single valid solution, is following conventions are generally applied. Rule number 1, every letter corresponding to the unique digit from 0 to 9, 2 letters can be represented the same digit. Rule number 2, first digit of any multi-digit number cannot be 0. For instance, in the puzzle TE plus ME equals to NET, neither T, M or nor N can be 0. Rule number 3, puzzle must satisfy all standard arithmetic rules. The solution is the assignment of the digit that make the equation mathematically correct. The strategy for solving cryptothem often involves analyzing the structure of the arithmetic problem, paying special attention to carry over the digits and the unit column. Key logical approach. Some helpful strategies point to solving these puzzles include leftmost digit. Studying the digit in the highest place value can reveal the presence of the carryover. In addition puzzles, the carryover is often 1. Unit column. Since the unit place does not receive the carry in front of any previous column, it is usually the easiest place to find initial clues and narrow down possibilities. Solving cryptothem. Let's apply these rules and strategy to solve some examples, starting with the addition puzzles. So, addition puzzle example: determine the values of letter X and Y in the following puzzle. Solution: first step, analyze the unit column. The sum 7 plus 5, that is 12. So, unit digit total is 2. So, the tens place digit get carry over 1. This tells us that the unit digit X plus 5 is 2, and so X minus 7. Now, analyze the tens column. The sum is 1, that is carryover, plus 2 plus x minus y, substituting x minus 7. So 1 plus 2 plus 7, 10. So the tens digit is 0 within the carryover of 1 to be 100 place. Since the 100 column is empty, in this case we consider y equals to 0. Now step 3 will verify 77 plus 25, 102, which satisfy the puzzle. So x equals to 7 and y equals to 0. This is how we are going to solve. So practice all the examples. Tips for solving cryptonyms. Start by examining the unit column of the often gives the first clues about the possible digit. Identify the carryover in the addition problem, then significantly restrict possible solution. Remember that each letter corresponding to one unique digit, no duplicate allowed. Work step by step, column by column, using the logical deduction. Next is multiplication cryptonym puzzle. After practicing addition based cryptonyms, we now turn to the attention of multiplication puzzle. These puzzles are slightly more challenging because each letter can affect multiple places in the product, requiring careful logical deduction. The basic rule of the cryptonym remain the same. Each letter represents the unique digit from 0 to 9. No multi-digit number can start with 0. All arithmetic rules must be followed and the final assignment of the digit must make the equation correct. Let's take an example here. Determine the value of the letter B in the following puzzle. So this is our puzzle. We have to determine the value of B. Analyzing the unit column. In the unit column, B into B must be end with the digit B. So B into B, that must be end with the digit B because that is equals to B here. Testing the possibility. Digit, we find that B could be 0, 1, 5 and 6. These are the digits where the square end with the same digit. So these could be the possible digits. Now test each possibility. If B equals to 0, 10 into 0, 0. But expected product is C0, so it's not valid. If B equals to 1, then 11 into 1, that is 11. But the expected product is C1, that is not valid. Now B equals to 5, then 15 into 5, 75. But the expected product is C5, so that's also not valid. Now if B equals to 6, 16 into 6, that is 96, which matches the expected product C6. So that is valid. Now deduce the solution. Therefore, the correct value of B equals to 6. Some multiplication cryptonyms may have the more than one valid solution. Any assignment of the digit that correctly satisfy all the rule of cryptonyms uniqueness, proper placement and arithmetic accuracy, consider correct. Tips for multiplication cryptonyms. Always start by examining the unit columns. Always start by examining the unit columns is often provide the first clue. Test all the possible digit that could satisfy unit digit requirement. Verify each candidate in the full multiplication or ensure the product matches digit the puzzle. Remember, the carryover values are important in the tens, 100 and higher columns. So analyze each place carefully. Now learning point 5.3, you have to practice all the questions. Next is summary. First is parity of the number. The number is even is divisible by 2 and odd is not divisible by 2. Parity is an algebraic expression. Sum or the product of even and odd numbers follow the rule. Even plus even, even, odd plus even, odd, odd into odd, odd, odd plus odd, even, even into any, that is even. Next is divisibility by 2, 4, 5 and 10. For 2, last digit should be even, means the unit digit should be even. For 4, last 2 digit divisible by 4. For 5, last 2 digits should be 0 or 5, or unit digit should be 0 or 5, and for 10 last digit should be 0. Divisibility by 3 and 9. 3 the sum of digits should be divisible by 3, and for 9 the sum of digits should be divisible by 9. Now general divisibility theorem, if the number is divisible by 2 number, it may also be divisible by their LCM. Digit roots, sum of digit repeatedly until the single digit obtained. Useful to check the divisibility by 9. Cryptonyms, arithmetic puzzles where the letters replace digit, each letter represents the unique digit. Next is divisibility by composite number. Use factorization to check the divisibility. Here we will use the factorization to check the divisibility by the number like 6, 12, 15, etc. Application of parity, help to solving algebraic expression and equation quickly. Check divisibility stepwise. Use the last digit, last 2 digit or the sum of digit for quick checking. Addition and multiplication rule. Parity rules can predict the result without complete calculation. Mathematical reasoning in cryptonyms, logical deduction is used rather than guessing to find digits. Digital roots as a verification tools can check correctness of addition, subtraction and multiplication. Importance of the learning of divisibility rules, speed up calculations, help in mental maths and simplifies problem solving. Practice make perfect. Frequent exercises with the number parity and cryptonyms strengthen number sense. Frequent exercise with the number parity and cryptonyms strengthen number sense. So here we end the chapter. In this chapter we have learned about the number divisibility rule. How can we check whether the given number is divisible by the number. We have also learned about cryptonym puzzle, how can we solve them. So all these things we have learned in this chapter. I hope all these things are clear to you. Now to practice it.